Okay, so for this lesson, we're going to write and graph exponential functions. Remember, a function is just anything written, y equals, and then everything after that. You'll see it commonly in the slope-intercept form. So there is a difference between a linear function, which is the one we're used to, linear function. Function. You're used to this one. It's y equals mx plus b. But an exponential function, that one is usually written y equals a times b to the power of x, x being the exponent. So it's still a function. You can write a table and you can graph it, but the graph does crazy different things compared to the linear function. A linear graph, it's going to have just a straight line. An exponential function is going to have a curve to it, either direction. Okay, so those are the main differences there. So let's look at these two tables. Let me take a picture. So here's two examples of two different functions. The first one being our linear function. You can see here our slope is 3 and we started at 2. So when the y-intercept is 2, the x is 0. Really easy, right? Because of our y-intercept, we know that. Yeah. And then our slope is up 3 over 1. So we go up 3 over 1. Make sense?
Yes.
You can also go backwards with that too. But you can see it forms a nice, easy pattern here of adding 1 and then adding 3. With an exponential function, okay, you have your y-intercept still at 2, 0. But you see the main difference is, let me get my other marker, yellow maybe, is now instead of the slope being plus 3 over 1, it's times 3. Okay, because of the exponent. Okay, so you're going to have 3 times 3 times 3, however many number of exponents there are. So when you create the table, you use your y-intercept, and then you're going to add 1 to the top, to the x value, and you're going to multiply times 3 on the y value. So that's the main difference you got to recognize. So let's go practice. All right, so let's look at this table. This is example 1. So for this example, what we're trying to do is create the rule, or the function, the formula looking thing. So it's going to say y equals, and we're going to find out what the rule here is. So let's look at the x. What changes from -2 to -1? We added 1, right? What about here? Added 1. Added 1. Easy pattern, right? Added 1. What changes from here to here?
You're multiplying.
Times 2. 4 times 2 is 8.
Yes.
8 times 2 is 16. 16 times 2 is 32. Yeah. So, I wrote this too close, so I'm going to move it down. So can we write a rule here? Y equals, what is our y-intercept? Where does it cross? At 0, and the y-intercept is 8, right? Yes. So you can say 8 times, because that would be your a value, and then b would be
1.
No, what is it going up each time?
Oh, times 2.
So 2 to the power of x. So then this is your rule for the function. Okay, so most of these you're just going to look at the table and decide what the rule is. Not too terrible, right? You have the rule written in your journal, right? Because that's what's going to help you. So make sure you have that written in your journal. The y equals abx.
Yes.
Yeah.
Y equals ABX.
Okay, let's do another one of these real quick. I'm going to do the practice down there at the bottom. All right, so again, let's look at this and see if we can figure out what the pattern is. So let's look at the x value. What happens from here to here? +1. What about there?
+1.
Got our pattern, +1 the whole time. All right, what about on the bottom? 3 times what?
3 times 3.
Okay, 9 times 3, 27?
Yes.
27 times 3?
Yes.
And we can assume that that's right. If you're ever not sure, you can always just grab your calculator and check it. So now we can write a function, right? Y equals, what's my y-intercept? 27.
27
Times, what's my
3x.
3 to the power of x?
3 to the power of x.
Yep. There you go. So now you have your rule. So it's called a function rule. Basically, it's describing to somebody who didn't solve it, this is how you would graph this function. Now, for fun, let me show you how you'd graph it. Okay, so you're going to go on the y-intercept here at 27. And then it's the slope is 3/1 for the first one, but then the next one is 9/1 and 27/1, so it's going to do a sharp curve up like that.
Wow.
Yeah, I mean, that's just a rough drawing. Okay, so actually now we're going to graph one. So it says, this is example 2. Graph the function y equals 2 to the power of x. It's nice they didn't give you a y-intercept. That's crazy. 2 to the power of x. All right, so first of all, looking at this formula, do we know what the y-intercept is?
2.
Nope. Remember, that's the exponent. That's that part. It's the number in front of 2, right?
Yes.
Which is what? Could I write this as y equals 1 times 2 to the power of x?
Yes.
Yes, doesn't change anything, right? So that becomes your y-intercept. So when the y is 1, x is 0. Does that make sense? Okay, so now we need to plug in. So what do we know our pattern, right? This is what? What's this pattern here?
Plus
Times what?
1.
No.
Not times 1. Oh, my bad. Times 2.
Yes, times 2.
Yes, times
So 1 times 2 is 2, right?
Yes.
So 2 times 2 would be?
2 times 2 equals 4.
4. Okay, now what about going backwards?
It'd be -2.
It would be divided by 2. It's not plus or minus. We went times 2 to go this way.
Yeah.
So to go backwards, we're going to divide by 2.
Yes.
So what's 1 divided by 2?
1/2.
And then what's 1/2 divided by 2?
1/4.
Very good.
Okay.
Okay, and then what's our pattern on top? +1, right?
Yes.
So this is 1, 2. This would be -1, -2. All right, now do I have a bunch of points I can graph?
Yes.
Yes. I don't know if I have a graph, so I'm just going to rough sketch it. And everything's above the y line, so I'm going to make my graph look like this. Actually, I'm going to scoot this line over a little bit too. Okay, because my first point, I can do 0, 1. Okay, so there's my first point. Then my next point is at 1, 2, right? So over 1 up 2. So that'd be about here. And then my next point would be over 2 up 4. So you can see how this does a sharp curve. If I go back and do the other two, the smaller ones, I'm at -1 and 1/2. right? So this is going to be negative 1 1/2 is about there, and then negative 2 1/4 is about there. So you can see how it starts very close to the line, and then it does a really sharp, and that's what an exponential function looks like on a graph. So when you hear that phrase, it increased exponentially, it's increasing at a very steep curve, where if it increases linearly, it's very gradual, and it's the same rate the whole time. So if you're talking about making money, do you want to increase exponentially or linearly? Linearly. Exponentially, because you're going to make money on top of money faster. Very good. All right. I think I can. This one. Uh-oh. Messing things up here. How do I make a copy of this? Ah. Copy. Hee hee. Okay. Let go. There. All right, so here's our graph we're going to do all this editing to. Although I lost my equations. Oh well. Lots of extra noise today. Okay, so there's the graph we did, and so this graph represents, I'm going to do it in red. This is the y equals 2x, right?
Yes.
We already did that one. So we need to graph y equals 3 times 2 to the power of x, and y equals negative 3 times 2 to the power of x. So you can make quick little tables. Do we know the y-intercept?
Yes.
Yep, it would be what?
-3.
The y would be
Negative
right here, 3
3
and 0. That's okay. The top one.
Top.
Okay, and then do we know what we're multiplying by?
Yes.
Which is by 2. So this would be 6. 6 times 2 would be 12. Divide by 2, so I'd get 3 over 2 here, and then divide that by 2, you'd get 3 over 4. Okay, and then what would our top number be? We're adding 1, right? So 1, 2, negative 1, negative 2. All right, so we can graph that one in a minute. Let's go ahead and do this one. All right, what was our y-intercept on this one?
-3.
Negative 3. So again, we're multiplying by 2. So negative 3 times 2 would be, and then negative 6 times 2 would be,
-12.
right, and then going the other way.
Be -2, 3/3.
Yeah. All the same, it just, this would be 1, 2, negative 1, negative 2. All right, all that makes sense, yes? So now let's graph them all. All right, let's graph the blue line first. So we're at 0, 3. So 1, 2, 3 is our first dot. And we go over 1, up 6. My graph's not going to be big enough. 1, 2, 3, 4, 5, 6. Over 1, up 6. Okay, and then over 2, up 12 is going to be way up there. So this is here, and this is there. I made those dots really big for some reason. Okay, so that one goes like this. And this is rough, guys. It doesn't have to be perfect. Okay, and then how do you think the green line is going to look compared to the blue line? Because they're very similar numbers, right? What's the difference? Negative. It's the same numbers, it's just negative. So technically, it's going to be the exact same dots as you see here. They're just going to be going in the other direction. So then the last thing it says is compare each graph. So you would tell me verbally what the differences are. So you can say that the blue line, and that's just because we colored it blue, and the green line are inverses of each other. And you compare it to the red line, and you could talk about it being slightly to the right, and in the middle, or, you just give me a verbal description of it. You would call it a vertical stretch. The red being a vertical stretch compared to the blue. And then the blue and the green line are reflections. I don't remember. I think I said inverses. Reflections is the better word. Make sense? That's it. Oh, wait, we got to talk about exponential growth model. So you need to make sure you have this key concept in your journals for sure. Okay, this is a model you're going to use a lot with word problems and finding the growth of populations. The growth or decay. We're going to do decay tomorrow, or next lesson. I think on Monday. So, when you had that formula a little bit ago, the function we had y equals a times b to the power of x. This is considered a growth function. And it's exponential growth. Okay? When a quantity grows exponentially, it increases by the same percent over equal time periods. So that's the difference. Instead of growing by equal amounts, it grows by equal percents. So that's why you get the exponential growth. So let's look at this and talk about all the vocab, what each thing stands for. So A is the initial amount. If you're dealing with money or population, it's the number that we started with. Okay. R is for the growth rate. Often this will be in a decimal or a percent, and you convert it to a decimal. Time period that's pretty self-explanatory, how long it takes. And then 1 plus R is the growth factor. Notice that the relationship between the growth rate and the growth factor, you're adding the 1. Okay, that's because you're growing, so it's going to be over 100%. Let's see here. All right, so let's just do example 4. Everybody got that in your notebook, that formula? You're going to be using it. So, example 4. We're talking about collecting cars. The owner of a 1953 Hudson Hornet convertible sold the car at auction. The owner bought it in 1984 when its value was $11,000. The value of the car increased at a rate of 6.9% per year. All right, so the first thing you want to do is write our growth 1 plus r to the power of t, our growth model. And then we're going to plug in what we know into this function, right? So how much was the initial value of the car?
11,000.
11,000. So you're going to plug that in where the A is, because that's the original amount. 1 plus, what is the rate that it increased per year?
6.9.
6.9%. So we have to change that to a decimal, and you do that by going to the left twice. So 0.069. And then per year. How many years? Oh, so this is A, because it just said write the function. So this is A. Just put T because it hasn't told us how long we're checking this out yet. And then for B, it asks you to say the auction took place in 2004. What was the approximate value of the car at the time of the auction? Okay, if it took place in 2004, what was the original year he bought it?
1984.
84. So what's the difference between 2004 and 1984?
20 years.
20 years. So we can say y equals 11,000, 1 plus 6, 9, all to the power of 20 years. And then you can use a calculator to solve this. So this would be 11,000 times 1.069 to the power of 20. Somebody with a calculator. So it will approximately, you'll get a decimal answer. We just rounded it. So the approximate value 20 years later is $41,778. You all know how to do exponents on your calculator, right? If you don't, let me know, I'll show you. I would do that first. I would do on your calculator, I would do this to the power of 20 and then multiply the answer times 11,000. So, did he make a good investment? He invested 11,000 and he sold it for 41,000.
Yes.
Yeah, he made some money.
30,000 profit.
Yep, $30,000. All right, let's look at example 3. Graph the functions y equals 3 times 2 to the power of x, y equals negative 3 times 2 to the power of x. And compare each graph, we have 3 graphs, to y equals 2x. That's the graph we just did, right?
Yes.
Let me go back and see if I can steal it. Out. Compound interest. Compound interest is the exponential growth for money. This is how investors make tons of money because they put money into accounts where it's making compound interest. So it's earned on the initial investment, plus every year they add the interest you made for that year, and then the next year it's on that added amount, whereas simple interest is always just on the original amount. So, example 5. When you put $250 in savings, that earns 4% compound interest annually, so yearly, and you don't make any deposits or withdrawals, how much will you have at the end of 5 years? So let's plug this into our model. Y equals, what's our initial amount?
250.
250. 1 plus, what's our rate?
Plus 4%.
So 0.04, because you make it a decimal. And how many years?
5 years.
5 years. So let's plug this in and see how much money he had at the end of 5 years. What is 250 times 1.04 to the power of 5? It's approximately $304.16. Didn't start with a lot of money, so it doesn't grow that fast, but it does grow faster than simple interest. And you just made money for it sitting there. Any questions on how to use this formula? Okay. This is 7.4. You're going to do numbers 5 through 38 evens.